packet scheduler developed by Senior NITK Surathkal to fight the Bufferbloat problem got merged into the mainline of the kernel in 2006. This team has built an open source network emulator for teaching and research, which has been adopted in several colleges and is supported by industries. He is a member of the steering committee of the NS3 consortium and the co-maintainer of traffic control and TCP modules in NS3. He is serving as a mentor for Google Summer of Code from 2017 till date for the NS3 organization and has been one of the organization administrators since 2021. He also served as an organization administrator for NS3 in Google Code during 2018 and 2019. He is a member of ACM, PIE, and a Senior Member of IEEE.
Thank you. I hope the mic is working. All right. Okay, so good evening, everyone. First of all, thank you for inviting me here for the talk at CNI. So when Professor Parimal has visited NITK, he did mention to me about CNI. Glad to be coming and delivering a talk. So when I was asked about the topic, I decided the topic that I have been working on from quite some time. And I have still active PhD students looking into this particular topic. So the thing that I have been working on is on trying to solve the problem of buffer bloat. I'll talk about it, what it is. Very simple thing to understand as to what the problem is, but then the solutions have been evolving for years. And one of the most important thing that remains is how easy is the solution to deploy. Solutions are there, but then we also want the solutions that can be easily deployed and the actual impact can be seen. So the title that I have chosen is the need for speed. All of us, we want low latency on the internet. And there are many ways by which you can actually cut down the latency, but I have chosen one of the approaches in this presentation is we can minimize the latency or minimize the impact of buffer bloat, which has a direct impact on the queuing delay aspect of the latency, because there are many aspects of latency that people can talk about, but we'll be talking about the buffer bloat. And I'll actually break down this word buffer bloat into what it means and how is it identified and what have been the work that people have done and what we have done and what is the current status of our work. So yes, I work at CS department at NITK, and this is a small center that we have, which is called Center for Open Source Software and Hardware. So we have a dedicated center because a lot of our students work on open source, and we have been actually contributing back to a lot of open source tools. For example, you might have heard about a tool called NS3. A lot of students from NITK since last 8 years have contributed modules to NS3, which are in the main line of NS3 today. So we have a dedicated center where we do a lot of open source activities. And this is a small little tool that we have developed from last 3-4 years, which we call it as Network Stack Tester. It's a Python wrapper built on top of Linux network namespaces to quickly spin off topologies for experiments. And you can play with almost everything that's there in the Linux kernel using this tool called Nest. So this has been built ground up at NITK. And currently, it's in use in 2 industries related to network. So they have been actively using it, and we have been actually giving our services to those companies for using this tool. That means whenever they want, they actually reach out to us, and our team gives services on how to use Nest and how to perform experiments. Say for MPLS, you want to have a quick topology that you want to spin off and just quickly run MPLS and LDP protocol to distribute the labels. You don't need to do too much. There are some ready-made examples that we can use. So that's that logo. Let's get into the topic for today. I'll quickly touch upon 2 important things, bandwidth and latency. And then I'll go about what are the current requirements that people have with our applications. We have a variety of applications. We have applications, instant messaging like WhatsApp, where the user is not tolerant for even a few milliseconds if 1 tick does not pop up, because we think, oh, if 1 tick has not come, probably network is not right. So we start opening Google. We start seeing whether my phone is connected or not, but that 1 tick is important. We don't really care about 2 ticks because 2 ticks is dependent on the receiver, but 1 tick is important to me. So I'm not ready to wait even for a few milliseconds for that 1 tick to come on WhatsApp. But if I'm downloading a movie, I don't really care about 20 minutes. Or if the same movie I'm downloading in separate machine, again, it takes 25 minutes, 5 minutes more than the previous one, we don't care about it. So somewhere minutes don't matter, and somewhere milliseconds is not tolerable. So we are in an era where the latency requirements are totally different from application to application. So how do you go about it? Then I'll talk about the problem. But the summary of the problem is right in front of you. Buffer bloat, if you have to simply define what is buffer bloat, it is the user suffering due to surplus buffering. So if you are watching a Netflix video or Amazon Prime video or YouTube, and suddenly the spinner comes in, your experience wouldn't be that great, right? So that buffering is something that actually causes poor user experience. And that's what is buffer bloat. The word bloat in English means more than necessary. So when you say buffer bloat, I'm talking about the problem where you have buffer. It's not the shortage of buffer that's the problem, but it's actually excessive buffer that's the problem. And that's why the word was coined as buffer bloat. Okay. Then we'll talk about reactive congestion control in TCP, which we use every day today. Every device that we use today. Oh, yes. So this is just the outline of the presentation. I'll actually tell you why this problem happens. So there will be a slide which will be explaining about buffer bloat. And I'll talk about reactive congestion control. So every device that we have, whether it's a mobile phone or a tab or a laptop or a desktop or a server, the TCP that we use right now is reactive in nature, which essentially means that until the network doesn't drop some of the packets, TCP doesn't reduce its sending rate. It just says, oh, I can send 20 packets. Let me now try to send 40 packets. Oh, I can send 1,000 packets. Let me now try to send 2,000 packets. So TCP always has a habit of going on increasing the sending rate until you actually don't see any packet drop from the network. So it's reactive in nature. It doesn't it doesn't respond in a proactive manner. So, oh, latency is increasing. Maybe something is wrong in the network. Maybe I should slow down. Those kind of characteristics don't exist in the TCPs that we use today. There are TCPs that actually look at the delay and conclude that I should reduce my sending rate. But those TCPs that nobody uses them today. The one that we use in our systems is called Cubic. The default in the kernel, Linux kernel, the default in many operating systems, including Windows, Macintosh. Cubic doesn't respond to congestion unless there is a packet drop. You don't drop the packet, it doesn't respond, right? So how all of this has an impact on all the latency sensitive applications. So how does buffer bloat and TCP cause problems here? Then what are the potential solutions? Potential solution is about you can manage your queue actively rather than reactively. So don't allow the queue to become full in the first place. Those algorithms are called AQMs. If you look at the Linux kernel, these algorithms are called Linux queue disciplines, but meaning is the same, right? Queue discipline is actually a broader word. It's also used for packet schedulers. Packet schedulers are also called Linux queue disciplines. So we will see the goals and challenges. Then I'll talk about two very popular algorithms called CoDel and PIE. Then I'll tell you how we identified a bug in the implementation of PIE in the Linux kernel. How did we go about fixing it? And then how did that effort led to a new algorithm being developed at NITK, which is called FQ-PIE? And then how did we manage to get that merged into the Linux kernel? And now it's been there in the Linux kernel since last 5 years. And at least 2 Linux distros are using FQ-PIE as a default algorithm in their operating system. So, and what is the current status on that? Now, this is the latest thing that's going on in the community. People have been talking about low latency, low loss scalable throughput. They also call it as L4S because there are 4 L's here. That's why they call it L4S is for scalable throughput. What are people doing about it right now? And what are the key takeaways of the whole 1 hour of session that we'll have is listed down there. So feel free to stop me at any point and tell me if something is not clear. I'll quickly run through these 4 delays. See, if you talk about Wi-Fi, if you talk about wireless, add another 2 slides to the delays, because these networks have another categories of delays that get added. But if you look at the fundamental latency characteristics, these 4 are going to be there even in wireline networks, even if you're not talking about Wi-Fi or cellular, right? So you have propagation, transmission, processing, and queuing. Now, propagation delay, a lot of CDNs already exist. Propagation delay says the distance between 2 entities divided by speed of light, right? So now what do? You try to bring the servers nearby, cache the data, use CDNs like Akamai, and bring the data nearer to the client. So the routing algorithms will say, oh, you are sending a query from Bangalore. We have the server in Bangalore itself who can respond to you. You don't need to route your packet all the way to Delhi or even to US. So you can cut down the propagation delays. Fantastic amount of work has already happened. Propagation delays have been, people have been trying to cut it down as much as possible. Transmission delay, the size of your data divided by bandwidth. Bandwidths have increased in the past. When I was doing my undergraduate, we never heard about things like 10 Mbps and all. But that's kind of the basic thing that we have on our phones today, right? So bandwidth has increased, and if your bandwidth has increased, your transmission delays can actually come down. Propagation delay, everything is multi-core. You can process simultaneously multiple packets. Each core can handle one packet because the internet characteristic says that each packet can be routed independent of each other, even if they belong to the same flow. So if I have 10 packets, each one of them can be put up in separate core and parallel processing can be done. But what's something that hit out in 2011 was we noticed that we have not focused on queuing delay. So a lot of the people so far were then working on throughput. For example, if you take a look at the Wi-Fi standards, what are the standards called? HT, VHT. What does it indicate? High throughput, very high throughput, and much later came high efficiency. Now, how do you define efficiency? Oh, we care about high throughput, but at the same time, we want latency also to be low. So you don't want only high throughput. You want high throughput, but also low latency. And this is where the engineering trade-off comes. You try to increase the throughput, your latency also increases. You try to cut down the latency, throughput comes falling down. So you have to see that your efficiency curve should be maximization of throughput and minimization of latency. And people realize that this is the one that we have not actually focused since quite a lot of time. The reason people did not think about this for a lot of time was because earlier memory was expensive. Today, if you try to buy memory, when I say memory, I'm talking about your main memory. When you try to buy main memory, it has become inexpensive. What's the RAM capacity that we have in the phones in our pocket today? Minimum 8 GB to 16 GB. What was the RAM capacity of the laptop that I used in my undergraduate? 512 MB. And where is 16 GB today? So, and look at the prices in the market. So basically what has happened is memory has become inexpensive, and that's why devices nowadays tend to have more memory than actually necessary. And that's where the problem of queuing delay started becoming more prominent. And one, network engineer or maybe a scientist at Alcatel-Lucent came out in 2011 and coined the word Bufferbloat and said, my device is buffering way too many packets than it should be. And it all started by looking at the home gateway that he had in his house. So he looked at the plot of the gateway and he saw that too much buffering was happening. And then he started understanding what is the reason. So that's what we will also see today. Why did this happen? Before we do that, there's a nice little plot that I always like to reproduce from Ilya Grigoryk's book. This is one of the finest books that I have read in computer network, which is called High Performance Browser Networking. And this is probably only one of those books that answers too many old questions that I was looking for. For example, why IPv4 is called v4 and why IPv6 is called v6. Like many a times we say, oh, IPv4 is called v4 because it has 4 bytes. But then that way the v6 should have 6 bytes, but it has 16 bytes. So why v4 is called v4? So this is one of those books that actually gave me all that answer. And this is also the book that tells you what is one Linux command to change the TCP in your kernel. Let's say you're not happy with cubic. You want to try Westwood in your kernel, just one command, and then you can change your TCP from cubic to Westwood. So this was on one side giving me all the information about internet's history, how internet has evolved. At the same time, it was giving me all the practical aspects. How do I play with the actual kernel in day-to-day life? So this is one of the finest book where I got this plot. So I have given the credits to that book here. What Ilya Grigory is trying to show is the latency plots that they got at Google. So he was a performance engineer at Google when he wrote this book. Now he's not at Google, but all these stats he's produced, what he says is on the x-axis, let's put the bandwidth and try to increase the bandwidth from 1 Mbps to 10 Mbps. And let's see what is the page load time, because that's also critical to Google's business, because how soon does the page load? So if you take a look at it, it's in the order of 3 seconds here. And as you try to reduce, if you try to increase the bandwidth, you can see that page load time does reduce. It reduces significantly over here, but try to take a look at it after 6 and 7 Mbps and 8 Mbps. It has kind of saturated. You are actually adding more and more bandwidth on the right hand side, but it's not actually impacting reduction in the page load time, because page load that you do, a web page that you load, is actually not throughput hungry, right? It's latency hungry. So it basically leads low latency rather than high throughput. And you can see any bandwidth that you stuff after 7 Mbps is not going to add any value to your latency. But if you take a look at the plot below, by the way, you have to be careful. The plot is in the reverse y-axis. So 20 millisecond is on the right and 200 millisecond is on the left. It's a reverse plot for you to understand that page load time keeps reducing if you reduce the latency in any way. So if you reduce the latency from 200 millisecond all the way to 20 millisecond, page load time will significantly reduce every time you reduce latency. So this is one of the finest plots that I found, and I always have this. Now let's take a look at the 3 categories that we are surrounded with today. The last one is the most interesting one. The first one says we have latency sensitive traffic. You can categorize online gaming, remote health monitoring services, IoT devices, VoIP calls, audio video conferencing, all of that into latency sensitive traffic. Their requirement is they need minimum latency. And you can put instant messaging, WhatsApp and all, everything in that. Now, if you take a look at this one, it's your file downloads, emails with attachments, image video sharing, backup services, OS updates. This doesn't require actually low latency. It requires maximum throughput. So this is orthogonal to what you want here. You want here low latency, here you want high throughput. But take a look at what is the last category. This is called streaming content, or it is also called the timely traffic, which actually talks about the services that we consume the most today, right? Netflix, Amazon Prime, YouTube and all. And what they need is not low latency or high throughput. They need low jitter and consistent throughput. So I just don't want the latency to be low. I want the variations in the delay also to be low. That means when I send a packet, when I send 2 packets or 3 packets, they should arrive at an equidistant gap so that jitter does not pop up. So I just don't want low latency. My requirements have now actually become a little larger. I need low jitter. Variations in the delay are not acceptable by these applications. Okay, that's one point. Second, they also don't need very high throughput. You give low throughput, no problem, but consistently keep giving low throughput, these applications would work fine. Don't think that YouTube and stuff like that requires a lot of throughput. It actually doesn't require a lot of throughput. But whatever throughput you give to this application, if you give it consistently, you won't get the spinner. That's the logic. So, and that's what matters to the users when they are watching this traffic, because they want good user experience. Okay, so now you can see there are 3 categories and the requirements are quite different, and the last one made it even more challenging. It says forget about just low latency. Low latency is fine, but I also don't want jitter, so keep it as low as possible. And throughput, okay, fine, give me whatever throughput you can, give the best possible, but consistently give that much so that I can ensure that the users get good quality of service. Now, why did the problem happen? The problem, as I told you, buffer bloat has nothing big. Buffer bloat is one of the simplest thing to understand why it happened. It just happened because memory prices became low. Memory became inexpensive. So what earlier a vendor would put it in a router memory, now they would put more memory because it's not expensive to them. So when they sell you a Wi-Fi access point, or when they sell you any networking devices, earlier the memory was expensive and they wouldn't stuff in too much of memory because that would increase the price for the end user. But now memory is inexpensive, so they don't mind stuffing more memory and telling you that, okay, see, I'm giving you more memory, and they can afford it because it's inexpensive. What ended up happening is that we started having bloated routers or bloated devices in the network. That means you have now a device that can actually buffer a lot of packets. And more importantly, your end devices, the phones, the desktops, the laptops, they are using a TCP, which says, I'm not gonna reduce until the network tells me to reduce. And how does the network tell you to reduce? Typically, network drops your packet. And then you know that, oh, network dropped my packet, I should reduce. And now when is the network going to drop your packet? Only when those bloated buffers become full. So let's say I have a bandwidth of 10 Mbps and I have a buffer associated with it. Once my 10 Mbps bandwidth gets saturated, the buffer starts filling up. When the buffer becomes full, is then I realize that my packets are causing congestion and I need to reduce my sending rate. But meanwhile, what do you do now with this huge buffer that you created? It will take a lot of time to drain this. And the amount of time that the packet waits in this queue is actually called the buffer bloat problem. The problem that happens because of excessive queuing delays. So what is buffer bloat? Simple summary, large queuing delays is defined as buffer bloat. The whole effort is very beautifully captured in the buffer bloat community. This is a website. I have taken a little old snapshot. Fantastic amount of information is available on that. If you want to read about it, please go and take a look at it. A lot of work has been put up there. Most of the work is open source and the code is available, solutions are available, and this community has been putting a phenomenal amount of effort in bringing awareness about this. And a lot of people have started adopting it. For example, the recent news, I'll share the article with Professor Parimal and Preetham as well. So you know that Starlink is picking up everywhere, right? So Starlink has recently adopted one of the solutions proposed by the buffer bloat community, and they have acknowledged that they were able to bring down the entire delays within 44 milliseconds, the entire RTT to 44 milliseconds. And that's great. I mean, satellite network having a latency of 44 milliseconds, fantastic, because you know the propagation delays can be really high. So even Starlink has adopted this solution, which is called FQ-CoDel. I'll talk about it later on. And our solution, what we have built, FQ-PIE, is like FQ-CoDel. So we are also telling people to try FQ-PIE and tell us whether that works for you or not. And currently we have received expression of interest from 2 of the big companies who have said that we want to test FQ-PIE. So that's where our efforts are currently. Now take a look at what happened. From 1980 onwards, this RFC 793 came. RFC 793 is the TCP RFC. RFC 791, yes, please. That's right. So what people do is, and that's what is what you are trying to tell is actually you are going towards this point. So what you are telling is, okay, you have a big queue, but why is it necessary for you to use it? Why don't you just virtually put a limit and say, okay, I'm not going to use more than that queue? That means you need to actively monitor your queue, right? So that's the solution. You can see I'm expressing the problem. You already predicted the solution. The solution is try. No, it's good. I mean, that means you are capturing whatever I'm saying. So the point is, that we will be actually actively monitoring the queue. But also let me tell you that there are other solutions also that you can think of. You can say, well, I will put a small buffer. That's one way to look at it. But then the right buffer sizing in itself is a huge problem. So much so that actually there's a professor in US, I can send you the link of his profile. His majority of the entire work that he has done and the papers he has written is what's the right size of the buffer? Because it depends, and your capacity is not fixed, right? Your capacity is variable in nature, particularly when you go to Wi-Fi. Your data rates keep changing depending on what kind of Wi-Fi signal you have and what kind of rate adaptation algorithm you are using. Your data rate doesn't remain fixed. Your data rate keeps changing. So based on one data rate, you buffer. But now the data rate shot up. Now this buffer will actually lead to underutilization because you only kept this much buffer. So that much buffer was good for 10 Mbps, but that much buffer is less for 100 Mbps, right? So that is where the right buffer sizing becomes a challenge. And that's why people said, okay, let the buffer be big, but I'll actively monitor it. So I'll talk about, and in fact, one of the solutions that I'm talking about is actively monitoring the queue, the one that we have here. Okay, so now let's take a look at it. See, queues are becoming bigger in size. Okay, but who is ending up using them? It's all the TCP algorithms that you see. And by the way, this is still very old chart. I got it from 2010 when I was doing PhD earlier in 2009 time. This chart came up, and I have not updated the chart. But this chart came from this very nice paper on IEEE communication surveys and tutorials, where it shows the evolution of TCP from RFC 793. Moral of the story is, today, which one is the most widely deployed one? This algorithm is the most widely deployed one. It's called cubic TCP. You can change it if you want. It's one line in your Linux kernel, and you can go to another TCP. There are about 10 TCP algorithms in kernel, but we don't use the other 9 because we don't know we can change it. But actually you can. It's just a single command, and then people will change it. But then I'm talking to the audience in IISc. A common man doesn't know what is TCP. So what is default is what is maximum utilized. Now, what is this TCP? It is a reactive TCP. It keeps on increasing the sending rate until there is a packet loss. But the packet will be only lost when the bloated buffers overflow, right? So the problem is on both the sides. First of all, you don't have somebody managing your buffer at the network level. Second side, your endpoints don't reduce the sending rate until the buffer does not become full. So problem is not only at the buffers. The problem is also at the way the endpoints are reacting to it. So you could either make your endpoints smart, or you could actually tell your buffers that somebody is managing them. Google has brought in another algorithm, new TCP, new congestion control algorithm, not TCP. I should not say TCP. It's a new congestion control algorithm called BBR. It was introduced in 2016-17. It is the algorithm that Google is using nowadays in YouTube, in their data centers, in GCP, all these places. It's BBR that is deployed. It's a congestion control that doesn't, wait for your buffer to become full. So they have taken an approach where endpoints are becoming more smarter. Other part of the community is actually going and saying, okay, let's do something better. Let's try to control the queues. Let's try to monitor the queues. Okay. Ultimately, if you don't have a smart TCP or a smart endpoint, you end up having very high queuing delays. All right. So now if you imagine this is a typical scenario, this is a nice article I recommend you to read. And part of my title comes from this title. You can see household bandwidth and the need for speed. This is a study done in Australian economy. And the study is very elaborate and very detailed. They take up one example that only 2 adults are staying in a house. What will be the bandwidth requirement? 2 adults with 1 kid. What will be the bandwidth requirement? 2 adults with 1 kid, 1 teenager. What will be the requirement? 2 adults, 2 teenagers. So like that, they have taken a pretty big spawn and then they have analyzed and said, okay, this is a bandwidth requirement. And what they came up is, they said typically a house in Australia or in that area where they did the survey will have multiple applications that meet 3 of the criteria that we discussed earlier. Some of the applications will be latency sensitive. Some of the applications will be latency tolerant. And every household will have streaming traffic. So now what happens is, their point is, if you have a common gateway that is taking all the traffic out, and if that gateway is choked because of a file download being done by anybody at house, the person who is having a streaming application will face a lot of poor user experience, because this bandwidth will be hogged away by the file download. At the same time, the latency sensitive flows will also be impacted because of this heavy file download. And sometimes what happens is, we all keep the default setting in our phones that update all my apps when Wi-Fi is found. You know that? We don't update it on our mobile data. Mobile data will get over if you update your app. So what we do, when Wi-Fi is available, and what happens is, without your knowledge, your phone is actually kept aside, not being used, but it's actually updating all the apps. And that all app updates that happen will happen in your house Wi-Fi. And knowingly or unknowingly, you will be actually bothering the person who is actually doing some important video conferencing or who is onto something latency sensitive. So that was a fantastic survey done, and they said future is going to be all about IoT, and these devices need low latency. You want to switch on a a light, a fan or something like that. You don't want your packet to be stuck in the gateway and then say, okay, let it take 5 milliseconds for the packet to go out and then something will happen. Although as human beings, we can't see the milliseconds, but Google's survey said that any web application that takes more than 300 milliseconds to respond, people don't visit that web application again, because they say that 300 millisecond people's tolerance is left. And imagine, we can't even see milliseconds. All that we see in our clocks is seconds, but milliseconds. Can't it sell? Well, it may or it may not, but probably not, in my opinion. The reason is WMM, which is called Wi-Fi multimedia, it just manages the traffic. That means if you have a high priority traffic, low priority traffic, medium priority traffic, it will give you different ways of treating each traffic. It will say, oh, you're high priority traffic, go this way. You're a low priority traffic, go this way. But who said that buffer bloat cannot happen for high priority traffic? If too much of high priority packets come in, then buffer will still be full. So point is, WMM will manage your traffic. WMM does not manage your buffer, right? You can segregate the traffic, but then one traffic can actually lead to bloating of the buffer, right? So you may update traffic priorities and filters frequently, but the kind of the computation that is needed to dynamically, we talk about this priority inversion. So keeping track of, who is actually getting starved, and then ensuring that you use priority inversion to kind of see to it that the starvation doesn't happen. But then how much amount of compute goes in and how many packets are coming to you every millisecond? So point is, there is a trade-off of the computation versus the kind of the system that you want to develop. So whether it is worth, and that's exactly what people have written. There's a nice article again on buffer bloat that covers these aspects, whatever I have exactly said. It's not me telling you, it's the whole buffer bloat community coming and telling that you can do WMM and you can do more sophisticated stuff, but then you should decide whether it is sufficient for you or not, or it is just better you go and solve the problem using directly managing the buffer rather than managing the traffic. You do traffic management, which people like to do it in Wi-Fi, but additionally just do more buffer management so that you can get rid of the buffer bloat problem. So this slide is only for that. You can see here, this is the question. What's wrong with simply configuring the QoS? I can use WMM as a QoS and I can solve the problem of buffer bloat. No, it wouldn't. And these are the findings of the community. They also did testing with VoIP, live online gaming, and they said that it doesn't work. Okay, your buffers will still remain bloated. So now we talk about the potential solution that you are coming up to. These algorithms are also known as queue discipline. So sometimes you will see words alternatively used. So first of all, what is the goal of these algorithms? Proactively monitor the queue to avoid congestion. Don't allow the queue to become full. Minimize queue delay, but ensure that you don't hurt the link utilization. This is where the engineering trade-off comes off. Okay. So imagine this water bottle in my hand is something that is a queue. And imagine that I have a capacity to pull out 1 liter from this part. And the water is being poured from the top here. What I want to do is, I'm pouring the water. I want this 1 liter to be fully saturated at any point of time, but I don't want this buffer to become full. So I have to allow the incoming rate such a way that it is not less than 1 liter, because if it is less than 1 liter, then my link is underutilized. Then you will say, okay, put 2 liters. Okay, if I put 2 liter, 1 liter will go, 1 liter will be queued. I don't want 1 liter to be queued. That's too much. So you would say, okay, then you just put exactly 1 liter. That's not possible. Can you control incoming traffic? You can't control incoming traffic. So what you do is you say, okay, let the incoming traffic come. I want to keep this full, but I'll allow little bit of queuing. That little bit of queuing will help me to ensure that the link remains fully utilized at any point of time. That means there's already some amount of packets that are waiting in the queue. As soon as link capacity becomes free, the packets will go and fill up the capacity again. But the queue should not be so much that my queuing delay becomes significant. So this is the engineering trade-off that AQMs try to give you. But again, AQM algorithms face some challenges. What are the challenges? What if your traffic is unresponsive? Now take UDP as an example. UDP doesn't respond to congestion signals. If it decides to send at 10 Mbps, no matter what you do, it just throws the packet. That's what I tell. UDP is spray and pray. Spray the packets in the network, pray that they will reach at the other side. No congestion control, no error control, no reliability, nothing. I want to send something, I'll send it, and I don't respond to any congestion signal. So if this kind of flows enter into the queue, you're going to find it very difficult to control buffers, because what will AQM algorithm do? AQM algorithm will drop your packet and hope that the other guy is TCP. So I drop the packet and I say, hopefully this guy will reduce because I have dropped the packet. But then you see it is UDP and it doesn't care about what you do. So this is where AQM algorithms might fail. So those flows are called congestion agnostic flows. Another problem is, even if your traffic is not from UDP or unresponsive, it can be bursty. Okay. And typically these burst flows are very short-lived. So for example, your WhatsApp message, okay, or your web application, for example, you're just doing a Google search, searching for IISc Bangalore. That search query that you put, okay, let's say a new announcement comes. Let's say some big thing is happening at IISc, like let's say alumni has come. Let us say, I think we got one very big news last year or last to last year about the hospital being donated. Let's say that comes, and now everybody starts searching about IISc Bangalore. A traffic comes in burst, but how much do you think is the volume of the traffic? The volume of the traffic is extremely low. Now, what is the problem? When the traffic comes in burst, I send, slow down, slow down, slow down, I am getting congested. But you know what? It doesn't matter to them because they are done with sending the traffic, because that was the traffic that they had to send. So there is no second time that they have to send the traffic. Everything got done in very short period of time. So my feedback from the network doesn't help the end host, because end host has already completed sending the traffic. So such kind of traffic can be harmful. So that's what I said. It is short-lived. Typically, it is low volume and it is bursty in nature. Search queries, ad mining, ads that come up in Google search, right on the right side, the ad mining, or for example, sometimes your interactive not interactive, your instant messaging applications, they can be bursty in nature as well, right? A lot of messages come in burst. How many of you have seen your phone kind of getting hanged when you open it after 10 hours of flight journey? Like your Wi-Fi is on, you're on airplane mode, you're flying 10 hours, you landed, got into the airport, Wi-Fi signal, and do you see that packets coming into your phone? Like your phone becomes unresponsive for a few seconds and you just say, let it finish all coming in, then I'll open up, right? That's kind of the burst. Now what happens is your phone just got switched on, but imagine the load on the access point that had to pump all this traffic to you significantly all at the same time. And in fact, once there was a problem statement listed by government of India, they started giving free Wi-Fi in railway stations. And there was a very peculiar pattern that they observed. Whenever train comes and goes, all the people sitting at the railway station, they get poor throughput. And when they did the diagnosis was all the people sitting at the station, assume they are not going to board the train that's coming in. They are just sitting, they are doing something. Now, when this train comes, a bulk of people come and they switch on their Wi-Fi and they connect to the AP. That leads to the burst for the AP. And they switch it on because they know that the station is going to come. So they switch it on like 2 minutes ahead. And now how does it happen? You enter into the station, you sync up with one AP, but the train is still moving. So you now hand over to another AP, then hand over to third AP, then hand over to fourth AP, and then do so on until your train stops. Same pattern when your actually train starts. And this was kind of significantly hurting the throughput that the people who were stationary sitting at the platform and using the internet. So this is one simple example of what burst can do to the stability of your network. It can actually disrupt your network stability. Okay. And sometimes it's very important for you to understand what is a temporary burst and what is a long-lasting congestion. Sometimes when you are hit with a temporary burst and you respond aggressively, that's bad because you fail to realize this was a temporary thing. And same time, if you wait too longer, then you say, oh, I thought this was temporary burst, but this is long-lasting congestion. It doesn't seem to be actually getting any better. So how do you balance the trade-off? How do you say that, okay, this is temporary? Oh, no, now this is persistent. So that is where some algorithms face challenges. And then there is a nice little mechanism described in RFC 3168, which talks about congestion signaling mechanism. It says, let's not drop the packet to inform the sender that I'm getting congested. You want to tell the sender that you are getting congested, right? As a buffer, as a router, as an intermediate device, you just want to convey to the sender, slow down. Why are you dropping the packet? Do it in an efficient manner. Because if you drop the packet has to be retransmitted all over again. So what they did is they just flip a bit in the IP header and they say, oh, okay, if this bit got flipped in the header, it means the router or the intermediate device is trying to hint that there is congestion building up in the network. So the TCP sender would say, oh, okay, I can see this bit flip. Thank you for not dropping the packet. I'm reducing my sending rate. So that was this mechanism. And the good part is it is deployed in all the operating systems today. However, this algorithm is not used. Why this algorithm is not used today? Because these algorithms are not yet used. So until you don't have somebody to tell you whether you are congested or not, how do you use a signaling mechanism? Somebody should first tell you network is getting congested, then you will carry the signal. But the person is not telling you that it's congested or not. And those AQM algorithms are now getting deployed slowly. So we spoke about these algorithms, but where do they sit in the system? Okay, so this is your NIC, the network interface card, which comes with its driver queue, which typically is provided by the NIC manufacturer itself. And this is your operating system stack. And you could be an endpoint. So your applications will be sending data to the IP stack, which will go this way. Or you could be an intermediate device, in which cases the packets will come from the NIC here. It will go to IP stack. All the processing will be done, and then it will be forwarded back here. So you receive the packet, process it, and send it out again. So you are an intermediate device, or you are an endpoint. You are sending the application traffic down here to here. Now, what is supposed to be focused is this two part here. So what happens is this is called queue discipline, or we can put AQM algorithms over there. Now, NIC is actually sending the packets out, and you are sending the packets from the application to the NIC, and assume that this driver queue becomes full. What will NIC do? When NIC sees that the driver queue is full, it does not drop the packet. It sends a back pressure signal to the earlier queue. So what it does is NIC sends a message to the OS saying that stop sending any more packets to me because my driver queue is full. And what does OS do? It stops sending any more packets to the NIC. After some time, when there is some space left in this queue, NIC sends a wake up signal to the queue discipline and says, let the packets come. And then the host OS operating system dispatches the packets from the queue discipline on the driver queue. This is how it works. There's a catch here. I have written something in red. So what happens is, I'll tell you, take a look at the two calls, stop signal, and then there is another one called wake up. Sending a stop signal is a no-brainer. Why? When do you send the stop signal? When your driver queue is full. The question is, when do you send the wake up signal? And why is that important to our discussion? Let's say you have one space available and you end up sending the wake up signal. The moment you do that, the next signal will be stop again. Agree? So what will happen? A series of stop, wake up will keep happening. So what most of the NIC manufacturers they do is they don't send up the wake up signal when there is only one queue or one space in the queue. They wait for some space in the queue, and this sum has not been standardized. So every NIC manufacturer will put it in their own way. Some NIC manufacturers will send the wake up call when they have space for 3 packets. Some will send the wake up call when they have space for 10 packets. Keep this in mind, and I'll explain to you how we identified the bug in the Linux kernel. This is the beginning of that story. Okay, the story emerges from here because we were experimenting with 2 NIC cards. I don't want to use the name of the companies. I'm on record. So we used 2 NIC cards and we found something very weird and we could not understand what's happening. And that's when we studied and we found, okay, this is the potential reason for happening. So let me go forward. Okay, and how ECN signal works is this signal, the one which I said, what does it do is you send the packet from the endpoint. It goes to a router that is getting congested. It will flip 1 bit. That flipped bit will be going to the receiver. Receiver will actually mirror that bit to the sender. And now the sender knows, oh, somebody is trying to tell me that there is congestion. But please remember my word, somebody is trying to tell me that there is congestion. Because ECN doesn't help you to identify where congestion is happening among these 3 routers. Congestion could have been happening here, or it can be happening here, or it can be happening anywhere. It just tells you there is congestion happening somewhere in the network, and you need to reduce the sending rate. But you also don't need precisely the information where congestion is happening, because the maximum speed what you can send is according to the lowest link on your path. Agree with me, all of you? The maximum speed that I will get as an end host will be the lowest, the slowest link on the whole path from this endpoint to this endpoint. So I don't care about where exactly is congestion. All that I need to know is there is congestion, and ECN does that. Okay, so let's talk about quickly now the first algorithm, which is already an RFC. It's called RFC 8289. This algorithm uses queue delay as a metric to identify whether am I buffering too much. So the moment packet enters, so imagine this particular table as a queue, and let's say I enter the queue from here. So NQ operation is happening here, and the DQ operation is happening on that side of the table. What this algorithm does is when the packet is enqueued, it doesn't do much, just attaches the timestamp. It says, oh, this is a packet that came, you arrived at this time. And when this packet is now going to be out DQ'd, it picks up the packet and says, okay, let me see how much time you waited in the queue. Because I know I put a tag on the packet when you came. So you came at time T1 and now you are going at T2. What is the difference between T1 and T2 is the time that you spent in the queue. And then it says a question, oh, did you wait in the queue more than 5 milliseconds? Because I don't want you people to wait for more than 5 milliseconds. That means maximum latency that I'm able to tolerate for queuing is 5 milliseconds. This is a configurable parameter called target that you can decide as a person who is deploying this device. You can say that, okay, I am running CoDel algorithm and my target is 5 milliseconds. If you're working on data center networking, 5 milliseconds is not a good one because data center networks operate in microseconds. So you might want to shift your target from milliseconds to microsecond and say, oh, I'm in a data center environment where microsecond is the RTT. I want only for you to wait till 10 microseconds, not more than that. So now you define this parameter and say, okay, this is how I calculated the queue delay, DQ time minus NQ time. Did your current queue delay become more than 5 milliseconds? Yes, 6 milliseconds. My current queue delay was 6 milliseconds. Oh, is this the first time that you are seeing this queue delay go above 5 milliseconds? Yes, I am seeing this queue delay go up for 5 milliseconds for the very first time. Then the question comes, is this a temporary burst or a congestion? Because till now, every time it was less than 5 milliseconds. Less than 5 milliseconds was acceptable to me. First time I shot up more than 5, I should not jump and say, oh, congestion. No, it could be a temporary burst. You don't want to hurt the packets. So what you do, you switch on a timer called interval and wait for 100 milliseconds. So what do you see? Oh, this packet waited for 6 milliseconds in the queue. And this is the first packet that waited for so long. Now let me start my observation period for the next 100 milliseconds to see whether all subsequent packets are also seeing more than 5 milliseconds or not. And if they do, then you conclude that it is not a temporary burst, it is a long lasting congestion. That means for continuous 100 millisecond, every packet was more than 5 millisecond. Now, why did this 100 millisecond come? What was the rationale behind selecting 100 millisecond in the algorithm? Typically, an RTT in the network is 100 millisecond. Average, the measurement studies on the internet have revealed typical RTT in a network would be 100 to 150 millisecond. And what you want to do is, when you drop the packet, the impact of reduction in the sending rate will happen only after 1 RTT. Because you just now drop the packet, right? You drop the packet now, the impact of this drop will be visible only after 1 RTT. So that's mean wait at least for 100 milliseconds. Don't jump to the conclusion that it is congestion. And wait for 1 RTT to see whether it's temporary congestion or a temporary burst or a full persistent congestion. So now you do this, and now you enter into the dropping phase if your current queue delay was above target for the entire interval. So this algorithm has 2 phases called dropping phase and non-dropping phase. The algorithm starts in the non-dropping phase, and it goes to the dropping phase only when 100 millisecond of period showed that every packet had a queue delay larger than 5 milliseconds. So they do this. Otherwise, if that does not happen, then you continue to be in the non-dropping phase and don't go to the dropping phase. Don't drop any packet and reset the interval timer if you had started the interval timer. But now let's go to the next slide and see what do you do after you go into the dropping phase. Do you go into the dropping phase and start dropping every packet? If you do that, then you are going to hurt the link utilization. So you don't want to be dropping every packet. You need to drop packet, but sensibly, only so much that link utilization remains full, but the sender also gets to know that they have to reduce. So what do you do in the dropping phase? First of all, drop this packet. After 100 millisecond, you drop first packet and increment the count variable, because this count variable tells you how many packets have you dropped so far. This was 0 till now. Now you dropped 1 packet. So count will become, are you with me? Count will become 1. When will you drop the next packet will depend on current drop time. So the next time I will drop the packet will be based on my current time, because I just dropped the packet, and interval divided by square root of count. Can you please tell me what is interval value? 100. What is square root of 1? 1. 100 divided by 1, 100. That means 100 milliseconds later will be my second drop. But when the second drop happens, count will become, now square root of count will change. It will no more be 1. Am I right? It will be what? 100 divided by square root of 2 will be approximately 71. Agree? So my first packet drop and second packet drop were spaced out with a gap of 100 millisecond, but the second and third one were spaced out with 71 millisecond. Third one and fourth one will be spaced out with even lesser. And if you still see congestion, eventually the CoDel algorithm will start dropping almost every packet if count variable becomes larger. Agree with me? Yes. So count becomes more and more, the frequency of drop will be more and more. The count value is lesser, the gap between 2 packet drops is also high. So now this works like this. Until when does it behave like this? Until it is able to bring down the latency less than target 5 milliseconds. The moment your queue delay comes less than 5 milliseconds, immediately you go out of the dropping phase and enter into non-dropping phase. You know what mistake happened in this? When CoDel goes from dropping phase, it has incremented the count. Let's pick up a value of count. Let's say 30 packets. Okay. How many packets it dropped? 30 packets. Waited for so long to bring the queue under control. Brought the queue under control. Went into non-dropping phase. Resets count to 0. But what if network became out of congestion only for a split period of time? Like we said, there is a temporary burst. There also could be a temporary idle period. Yes or no? So I learned that I have to drop many packets. I did learn, but I unlearned everything when I reset the thing. And you know what we identified in one of our experiments of CoDel? This is an experiment done by us in CoDel in the Linux kernel as well as NS3. Look at this CoDel behavior. And by the way, we had 200 packets queue capacity in this chart and 10,000 packets capacity in this chart. Take a look at what CoDel does. It utilizes full queue and it takes around 20 plus seconds to bring the queue under control. It is able to bring the queue under control. The moment it brings the queue under control and shifts from dropping phase to non-dropping phase, it unlearns everything about the count variable And when the congestion builds up again, it again starts that 100 millisecond counter, and it again starts using this equation. This leads to queue fill up again. And you know, the best part of this whole experiment was we had 5 senders which were responsive in nature, and we had just 1 sender that was not responding to congestion, and it ended up making queue full. The entire buffer bloat solution was null and void because 1 unresponsive flow and you are out of your control. And you can see this periodic repeats. So it comes out of the dropping phase, enters into dropping phase again queue becomes full and repeats. Maybe people said, Mohit, where is buffer bloat in this? Just 200 packet. You say buffer bloat, take bigger queue. Okay, we took 10,000 buffering capacity. That's sufficient. 10,000 buffering capacity, CoDel fills up the queue, brings it under control, fills up the queue again, brings it under control, fills up the queue again. So we worked with the community and we came up with another algorithm called Cobalt. Cobalt has a full form called CoDel Blue Alternate. The paper is here. You all are welcome to read it. And you can see it is not our idea. It was actually idea of Jonathan, but implementation was totally ours. And we were telling him that, okay, this is a problem. So he solved the problem in Cobalt, and you can see Cobalt has much better queue control than CoDel. But Cobalt, one flaw we found out in Cobalt is it doesn't behave properly until it also fills up the queue at least once in its lifetime. So you can see Cobalt also filled up the queue at least once, but later on it was under control. Here also you are not able to see it, but actually Cobalt is actually walking same line here, but you can see Cobalt comes down and then it remains like this. So this was one paper which got into IEEE Landman 2019, and then now Cobalt issue is also being worked upon, and already new fixes have come. It became slow because of pandemic. Everybody was kind of, in their own problem. So we had kind of stopped this work, but we are picking up this work. This was CoDel in quick nutshell. I don't want to take too much time, but then came another alternate, which is actually RFC 8290. It's called FQ-CoDel. So what you do is what they said is, one UDP flow can disturb your entire functionality. So what did they say? Let's do one thing. If you have 5 TCP and 1 UDP flows, put all of them in separate queues, virtual queues. But how can you segregate them into queue? So we applied a classifier, which is called the flow classifier. So we take up 2 IP addresses, source IP, destination IP. We take up source port, destination port, and the protocol number field in the IP header. So we take these 5 pieces of information and we apply hash algorithm. So if the packets are coming from the same 5 combination, they'll all be put up in one queue. If they are different, if they have even one field different, IP is different or port number is different or protocol field is different, it will be in a separate queue. So this FQ-CoDel has been put up now in almost all Linux distros. So if you are using Ubuntu, do you use Ubuntu? Some of you use Ubuntu. Ubuntu by default has been using FQ-CoDel now. So that means already the active queue management algorithm is in your systems. And many Linux distros now support FQ-CoDel. Some of them have actually made it default. Some of them give you as a configurable option. You can enable it by default. Okay. So this was one algorithm. In fact, 2 that I spoke. And if you look at it, in fact, 3. I gave you the description of CoDel. Then I told you briefly about Cobalt. Then I told you about FQ-CoDel. Now, looking into the time, we have about 5 minutes. So what I'll do is I'll tell you about PIE. What is PIE? PIE is exactly like CoDel in terms of using the metric. It says, yes, queue delay is a good metric. So they also started using queue delay as a metric. However, CoDel operates at the DQ time, because what CoDel says is, oh, you got enqueued here and you are getting DQ'd. This is the time that you spent. And it decides whether I should drop the packet or I should allow the packet to go. PIE brings the operation to the NQ time. What PIE says, no. I will not allow you to enter into the queue if I see that my queuing delay is already not acceptable. If I see my queuing delay has already crossed the target, then I'll not allow you to enter into the queue in the first place, right? So it's putting the check at the NQ time, whereas CoDel runs it at the DQ time. That is one change. Second thing is the PIE algorithm was proposed by Cisco. They said target of 15 millisecond is good, but nobody asks you. You can make it 5 millisecond. PIE is supposed to work. What this parameter tells PIE is, if I tell you to control at 15 millisecond, you should work like that. If I tell you to control at 1 millisecond, you should work like that. So PIE algorithm will automatically adjust depending on what target you give. And what PIE does is, CoDel algorithm used to run on every packet DQ. whereas PIE algorithm runs only once in 15 milliseconds. So every 15 milliseconds, it takes a snapshot of the queue. So after 15 milliseconds, oh, how is my queue now? After 15, so basically if T1 is 0, then T2 will be 15 milliseconds. T3 will be 30 milliseconds. T4 will be 45 milliseconds. So every 15 milliseconds, it checks the queue. It doesn't operate basically looking at every packet. Okay. And of course, it is built on a very old technology. I'm pretty sure you people might be aware about PI controller. So PI controller is in popular use everywhere right now in the industry. All our real-time systems use PI controller. So this is a very old technique proposed by Vishal Mishra. He was the first one to bring PI controller into AQM category. Cisco built upon this and made PIE. So that's why you can see PI controller was the original algorithm. Enhanced is the algorithm that Cisco made and made it as an RFC. So this is another algorithm. And here the incoming packet will be dropped if your drop probability here, which you calculate, is greater than a random number R. So this is why this algorithm is called probabilistic in nature. So whether the packet will be dropped at the NQ time or will not be dropped depends on the probability. Whereas CoDel is a deterministic algorithm. Why deterministic? If you dropped one packet, you know when to drop the next packet because that equation tells you that the next packet drop should be after so much time. Here, there is no guarantee that the gap between two packets will be 100 millisecond or 71. Two back-to-back packets also may get dropped, or two packets may have a space of, let's say, 200 milliseconds. You never know. But what is this equation doing? This equation in nutshell, I'll explain to you. My target is 15 millisecond. I want my queue to be operating at 15 millisecond. Am I on the lower side or am I on the higher side? So that is called the diff from the target. So your stable operating point is 15 millisecond. How far you are from your desired operating point? 1. And what is the trend of your delay? That means you are sampling every 15 millisecond, right? Are you inching towards your desirable range or are you moving away from your desirable range? Let me give an example. You all can understand. 15 is my target and currently I am at 20. So what is the diff? 5 milliseconds. My first sample is 20. Second sample shows that I am at 18 and third sample shows I am at 16. So what is the trend of my current delay? Is my delay going towards the desired range or is it going away from the desired range? It's going towards the desired range, right? These two parameters are taken into consideration, which is my current delay and target. What is the difference? And my current delay and my old delay, where am I? And you apply the PI control parameters to these two to kind of bring the error so that you know where is the error and you try to fix the next cycle in that error and try to bring the whole algorithm to the stable operating. Okay, so now there was one big part in this algorithm. How do you calculate this queue delay? One thing they said, do it like CoDel does. One of the recommendation by the authors of PIE was calculate queue delay like you do it in CoDel. But there was one more recommendation called Little's law. What they said, oh, current queue delay you can find out easily. See how much queue is full divided by DQ rate. So if you know there are 20 packets, or let's say, let's not use the word packet. Let's say there are 20,000 bytes in the queue and you know the departure rate. So you know how much time it will take for these 20,000 packets to go out. That is estimation. So you can use Little's law to estimate. This is where the problem was. They recommended this as a default part in RFC 8033, and this was an optional feature. But what we identified as a bug in the Linux kernel implementation was, remember this diagram? Yes. NIC, buffer becoming full, sending the stop signal. And then when does it send the wake up signal? I told you. When some space is there, right? What we noticed was happening in the kernel, when NIC was sending the wake up call to QDiscipline already had packets ready to be sent. It just dispatched everything that it could until the next stop signal comes. So assume there are 3 packet worth of spaces here. NIC says, let the packets come. This QDiscipline will dump 3 packets instantly, almost instantly. And what PIE ended up doing is, it took the departure rate from this queue to this queue rather than taking the departure rate out from the NIC. Now listen, you have a NIC which is operating at 10 Mbps. If I have a water bottle of 10 liters, can I drink more than 10 liters? If this bottle is half liter, can I drink more than half liter? But what our experiments were showing in the Linux kernel, this is 10 MB we have configured in our experiment. It says 12 MB departure rate, 18 MB departure rate. And we are like, How is it even possible? We have configured 10 MB. How can it be more than 10 MB? Then we realized, oh, the departure rate variable that we were printing from the kernel was actually not calculating the departure rate here. It was calculating departure rate here. And this could be anything because this is an internal transfer. This is not restricted by your network. So then we identified, we reported to the Linux community. They acknowledged it. They said, what is the fix? And it was easy for us to say, use second technique like CoDel, because CoDel was already there in the kernel. So we just said, do it like CoDel. And they said, can you submit the patch? And we submitted the patch and they accepted the patch. So now in last 4 years, this bug has been fixed. Now, if you calculate, you will get proper throughput. You don't see wrong values. But we saw that there was still problem in PIE because of UDP flows. By the way, there's a paper on this whole thing. This bug that we identified is filed in a journal, Computer Networks Journal, revisiting design choices in Q discipline, the PIE case. And we were explaining here that our expected QDIS backlog was 180 KB, but see the values that were coming with the bug. But after fixing the bug, all the values were within 180 KB range. You can see all of them are in 180 KB. These ones are like 800, 900 KBs and all. And this one is okay, but you can see again, this one is also more than 200. This one is like around 450. So this was with the bug. This is after the bug, and the whole things are written here. Last thing, like we have FQ-CoDel, our team implemented FQ-PIE, and this was the experiment with normal PIE, where Google's new algorithm, BBR, we had 2 flows, cubic, which we use every day, we had 2. And what we showed was these 2 BBR flows were being unfair with these 2, and you can see these 2 are not getting the throughput. Actually, they should be having 50% throughput. All of them should be equally sharing the bandwidth. Now, after we applied the FQ-PIE algorithm, you can see this is the whole behavior. So that means all 4 of them are now sharing almost same bandwidth. So we were able to bring fairness after FQ-PIE. Now, what's the current status of FQ-PIE? It's already there in the kernel. It's already there in NS3 if anybody wants to test it. We have taken one more step. Your feedback is much appreciated if you get any time. We have published the first internet draft on FQ-PIE. So we have pushed it to IETF, and our goal is to get an RFC number for this is an experimental category, so that more people can actually deploy it and then give us the feedback. So this is where we are currently. Now I'll skip this part in the interest of time, but I'll have a nice slide to summarize as to what is the current situation. So FQ-CoDel is currently the most widely deployed and default in Linux distros. FQ-PIE is available in Linux, and it is used by some of the Linux distros as default. And there are other old algorithms, which I did not cover today because they are not necessary. They are 1993, 1999 algorithm, but they are still very popular. I teach them in my courses. And a couple of companies who are very popular, again, not naming them because we are on record, they use still these old algorithms. Okay, so they are still relevant. There is a very popular algorithm called smart queue management instead of active queue management, which is called Cake, and it has been developed only for your home gateways. So you have a home Wi-Fi router, so that is where this algorithm runs. It's called Common Applications Kept Enhanced, and it's a part of the Linux mainline, and it is much more sophisticated. It has AQM inbuilt, but it has ACK filtering, bandwidth shaper, DRR, deficit round robin, plus packet scheduler, and very complicated algo. There is a nice company product called LibreQOS, which actually leverages FQ AQM. You can remove this AQM and put CoDel or PIE because both of them are FQ based, and you can improve your quality of service for ISPs and end user. And one algorithm that I skipped here in the interest of time, if you're interested, you can always reach out to me, and I'm happy to talk about this new initiative that combiningly has been brought out in the market by Cable Labs and Nokia about low latency, low loss, scalable throughput. This is being currently tested in Apple. So if you are having recent products of Apple in the last couple of years, you are knowingly or unknowingly using L4S, and even Samsung and some people have been doing active development. There are some papers about L4S by Samsung also that I have read. Apple has already mentioned in their annual performance these things that L4S is actually giving them good thing. But keep in mind, L4S, even though I did not talk about it, L4S requires you to control the end devices and the network. So if you are a company like these, then you can deploy L4S. But if you are only an ISP, then you can do something at the network side, but you will need cooperation from the end host part. So if you, or if you're a company that only controls end host, even then L4S is challenging for you because you need then cooperation from the ISP part. So those people who are testing, they have the network under control also. They also have the end devices under control, and that's where L4S is being deployed. But yeah, I could not cover that in depth because of time. But I hope that's it from my side. That's it. I think we overran by a few minutes, but that's it from my side. I hope I was able to give you some idea about why this area is important and a little bit of glimpse of what we have been able to do. So if there are any questions, I'm happy to take them. Oh yeah, so this has a deep root inside, you mean to say about this one, right? Yeah, so this has direct connection with how TCP increases the congestion window. So what happens is TCP in the slow start phase, when we work with it, it actually doubles your congestion window, right? So this algorithm is highly tailored to work fine with TCP-like flows. So this square root comes from its connection with TCP, deep connections with TCP. You might have heard. Yeah, of course. Yeah. All our time, this was the basic thing. So there was a mathematical model, I think, that you might have followed. That is where it comes from. So like square root of 3/2 into C wind, something like that. So that is where the whole algorithm evolves. And this was done to see to it that the way you increase congestion window is the way you respond to the packet losses. Sure. Oh yeah, there are many. So for example, the BBR algorithm that I mentioned, right? So this is the V1 that we used because that's available in the kernel. There was BBR V2, there's BBR V3. So the BBR algorithm actually doesn't depend too much on the network feedback. It has its own calculations. If you look at the internet draft of BBR, they try to predict whether you are congesting the network at your side itself. So there are two sides of the debate. Some people have said that let's not take any feedback from the network and try to derive our estimations. But some people said the best feedback can be from the network that is actually getting congested. So because the network knows whether it is congested or not, you can only make a prediction. Now the things in data centers are a bit tricky, in a way sometimes simplified. You own the network. You control the whole network in your data center. So you kind of know what are the resources that you're provisioned in the data center, right? You know what is the capacity. You know which link is what speed, right? You know the entire topology. You know at a high level that these are the resources I have provisioned in the data center, but you can't do that at a global scale of the internet because you don't know where is the bottleneck and what is the capacity of the bottleneck. So you can't get a global picture of what's happening all over. So that makes challenging for you as an end host to kind of keep predicting whether the network is congested or not. It will be much better if network itself could give you explicit signals that I'm getting congested, and then you say, okay, once I get that kind of notification, I'll respond. Until then, I'll just assume that network is fine because if it has problem, it will complain. But data centers, your life is okay. You can make conclusions at the endpoint because you kind of know what your network resources are and what your provisions are. So you can say, okay, I know this is my bandwidth provisioned here. This is what my capacity is. So I can make some assumptions. Although not so easy the way I'm saying, but it's relatively easier than doing that. And that time, since data centers have pretty good speed and they operate at microseconds level, this explicit signal business can be a little more. So it will be overkill for you. Like the network has to tell you, then you respond. So that computation, like running AQM algorithms in the data center per packet, doing so much of computation, doing drop probability calculation at that high speeds is actually sometimes not good, is what people have recorded. So they say it's better you do congestion control at the endpoint in data centers. But when it comes to the internet in general, you better take feedback from the network. I mean, was that your question? Did I understand it correctly? Okay. Yeah. Oh, yeah, sure. This one. So this is supposed to be the way we should have calculated the departure rate in the kernel. Oh, the point was this would have required much more of an effort for us to submit the patch than going towards the second one. So we didn't want to spend too much time because the community had acknowledged already that, yeah, there is a bug and we wanted to fix it. So what we did is, and another one more thing is, I'll tell you, RFC actually recommended both the approaches. So when we went with the second approach, the community was okay because we said RFC itself has given us one more approach, right? So that's why we didn't bother about it. However, answering your question in little more detail, I have a PhD student who actually is working on this average departure rate to be calculated properly over here at the NITK level. And we also have developed one more version of PIE that's also available in Computer Communications Journal. We call it as Minstrel PIE. And what we try to do over in Minstrel PIE is we smartly play with this departure rate, provided you calculate it correctly, first of all. So that fix we are doing first. So we now have an actual departure rate. And once I know my actual departure rate, which can fluctuate, actual departure rate never remains fixed. It fluctuates depending on the load on the network. What we try to do is we have made this parameter adaptable. So what we tell is, if my average departure rate is consistently showing me that link is always saturated, that means my network is already loaded. So what I do is I try to bring down this parameter from 15, and the lower bound is 5 because CoDel has shown to work well with 5. PIE shows work well with 15. So we have taken 5 and 15 as a boundary and said, keep lowering it until we see that departure rate gets affected. And we keep lowering it, we keep lowering it. And if we go till 5 and we still see our departure rate is not impacted, so now you get a better trade-off. Your utilization is kind of saturated and you are trying to push your queue latency lower. But if we see that in the quest of reducing the target delay, if our departure rate is getting affected, then we again come back and follow a binary approach. So how do you go up? You take a binary approach and you quickly go up and say, okay, so that's called Minstrel PIE. That's captured in one of our papers called Computer Communication. But that's only true so long as you are able to accurately estimate these things. And since this has been working fine in the kernel, we didn't want to again go back and say, okay, one more approach. So we just kept it simple. That's it. No other reason.
Thank you for the talk.
Thank you so much. Thank you.
So, refresh my